Limiting transformer capacity to 50 kV or less is driven by several key factors, primarily safety. Transformers exceeding 50 kV present significant electrical hazards due to the escalated currents and voltages involved. Secondly, smaller transformers often exhibit greater efficiency, especially when operating at lower load levels. Thirdly, the cost factor plays a role as smaller transformers generally prove more economical to manufacture and install. Fourthly, standardization contributes, with 50 kV emerging as a standard rating for distribution transformers, which streamlines replacement and maintenance procedures. Fifthly, protection mechanisms differ. Transformers below 50 kV frequently benefit from primary fuses, whereas larger transformers necessitate more intricate and costly protection schemes. Exceptions to the 50 kV limit do exist under specific circumstances. In rural settings characterized by extended distribution lines and low load densities, transformers up to 75 kV might be employed to mitigate voltage drop and enhance power quality. Certain industrial applications mandate larger transformers such as 75 kV to fulfill their unique power demands. In exceptional cases, utilities or regulatory bodies may authorize the installation of transformers surpassing 50 kV in residential or commercial zones, provided justifications stem from engineering studies and rigorous safety assessments. These exceptions are typically assessed individually, emphasizing thorough evaluation of safety, efficiency, and other pertinent considerations. Now let's delve deeper into each of these aspects. Regarding safety, the increased current and voltage levels in larger transformers pose heightened risks of electrical shock, arc flash, and equipment failure. Proper grounding, insulation, and overcurrent protection are crucial, but the inherent risk associated with higher energy levels remains a primary concern. Considering efficiency, smaller transformers are generally designed to operate more efficiently at lower loads. This is because the core losses, such as hysteresis and eddy current losses, become proportionally more significant as the transformer size increases. By limiting the transformer size, utilities can minimize energy losses and improve the overall efficiency of the distribution system. The cost factor is also significant. Smaller transformers require less material and are simpler to manufacture, resulting in lower production costs. Installation costs are also typically lower due to the smaller size and weight of the equipment. Standardization provides numerous benefits, including easier replacement, reduced inventory costs, and improved interoperability. By adhering to a standard rating of 50 kV, utilities can streamline their operations and ensure that transformers can be easily replaced in the event of a failure. Protection is another crucial consideration. Smaller transformers can often be protected by simple primary fuses, which are relatively inexpensive and easy to install. Larger transformers, on the other hand, require more sophisticated protection schemes such as circuit breakers and protective relays, which add to the overall cost and complexity of the system. Let's now consider the exceptions to the 50 kV limit. In rural areas, the long distribution lines and low load densities can result in significant voltage drop. By using larger transformers, utilities can reduce the voltage drop and ensure that customers receive adequate voltage at their service entrances. However, this must be carefully balanced against the increased risk of electrical hazards and the potential for higher energy losses. Industrial applications often have specific power demands that cannot be met by a 50 kV transformer. For example, a manufacturing facility with heavy machinery may require a larger transformer to provide the necessary power. In such cases, utilities may grant an exception to the 50 kV limit, provided that the installation meets all applicable safety codes and regulations. Special circumstances may also warrant an exception to the 50 kV limit. For example, a hospital or other critical facility may require a larger transformer to ensure a reliable power supply. In such cases, utilities will typically conduct a thorough engineering study to assess the risks and benefits of installing a larger transformer. It's important to note that any exception to the 50 kV limit must be carefully justified and approved by the relevant regulatory authorities. Utilities must demonstrate that the increased capacity is necessary to meet the customer's power demands and that the installation meets all applicable safety codes and regulations. Now, let's address some common questions related to transformer capacity limits. Firstly, what is the maximum transformer capacity allowed in residential areas? The maximum transformer capacity allowed in residential areas varies depending on local codes and regulations. However, in most cases, the limit is 50 kVA or less. Secondly, can I install a larger transformer if I have a large home with high power demands? In some cases, it may be possible to install a larger transformer if you have a large home with high power demands. However, you will need to obtain approval from your local utility and ensure that the installation meets all applicable safety codes and regulations. Thirdly, what are the potential consequences of installing a transformer that is too large for my needs? Installing a transformer that is too large for your needs could result in several negative consequences, including increased energy losses, higher electricity bills, and a greater risk of electrical hazards. Fourthly, how can I determine the appropriate transformer capacity for my home or business? The appropriate transformer capacity for your home or business depends on your power demands. You can consult with a qualified electrician or electrical engineer to determine your power requirements and select the appropriate transformer size. Fifthly, are there any new technologies or developments that are changing the way transformer capacity limits are determined? Yes, there are several new technologies and developments that are changing the way transformer capacity limits are determined. For example, smart grids and advanced metering infrastructure are providing utilities with more data about customer power demands, which can be used to optimize transformer sizing. In summary, limiting transformer capacity to 50 kVA or less is driven by safety, efficiency, cost, standardization, and protection considerations. Exceptions to the 50 kVA limit may be granted in certain cases, such as in rural areas, industrial applications, or special circumstances. Any exception must be carefully justified and approved by the relevant regulatory authorities. The NEC 2017 and subsequent editions provide detailed guidance on transformer installation and protection requirements. It's also important to understand the implications of exceeding these limits. Exceeding the 50 kVA limit without proper justification and approval can lead to code violations, safety hazards, and potential equipment damage. Therefore, it is crucial to consult with qualified professionals and adhere to all applicable regulations when selecting and installing transformers. Now let's dive deeper into the technical aspects of transformer protection. Transformers are susceptible to various types of faults, including overloads, short circuits, and ground faults. Overloads occur when the transformer is subjected to a load that exceeds its rated capacity. Short circuits occur when there is a direct connection between two or more conductors, such as a phase-to-phase or phase-to-neutral fault. Ground faults occur when there is a connection between a conductor and ground. The protection scheme for a transformer must be designed to detect and respond to these faults quickly and effectively. This typically involves the use of fuses, circuit breakers, and protective relays. Fuses are the simplest and least expensive form of overcurrent protection. They are designed to melt and interrupt the circuit when the current exceeds a certain level. Fuses are commonly used to protect small transformers and individual circuits. Circuit breakers are more sophisticated than fuses and can be reset after they have tripped. They are typically used to protect larger transformers and main distribution panels. Protective relays are electronic devices that monitor the current and voltage in the transformer circuit. They are designed to detect faults and trip the circuit breaker or other protective device. Protective relays are commonly used in large industrial and commercial installations. The selection of the appropriate protection scheme depends on several factors, including the transformer size, the type of load, and the applicable codes and regulations. In addition to overcurrent protection, transformers also require protection against overvoltage. Overvoltage can occur due to lightning strikes, switching surges, or other transient events. Overvoltage protection is typically provided by surge arresters, which are designed to divert the excess voltage to ground. Now, let's discuss the different types of transformers. Transformers are classified based on several factors, including their construction, their voltage ratio, and their application. Regarding construction, transformers can be either dry-type or liquid-filled. Dry-type transformers use air as the cooling medium, while liquid-filled transformers use oil or other insulating fluid. Liquid-filled transformers are typically used for larger applications, as they can dissipate heat more effectively. Regarding voltage ratio, transformers can be either step-up or step-down. Step-up transformers increase the voltage from the primary to the secondary winding, while step-down transformers decrease the voltage. Regarding application, transformers can be used for a variety of purposes, including power distribution, voltage regulation, and isolation. Power distribution transformers are used to step down the voltage from the high voltage transmission lines to the low voltages used in homes and businesses. Voltage regulation transformers are used to maintain a constant voltage level, even when the load varies. Isolation transformers are used to isolate two circuits from each other, which can be important for safety or to reduce noise. In conclusion, understanding the factors that influence transformer capacity limits, the exceptions to those limits, and the various protection and application considerations is essential for electrical engineers, electricians, and anyone involved in the design, installation, or maintenance of electrical power systems. Adhering to the NEC 2017 and other applicable codes and regulations is crucial to ensure the safe and reliable operation of these vital components of our electrical infrastructure. Remember that working with electrical equipment can be dangerous, and it is always important to consult with qualified professionals before undertaking any electrical work. Proper planning, careful execution, and adherence to safety protocols are essential to prevent accidents and ensure the longevity of your electrical system.